Great. So our next speaker is Nicholas Rubin from Google, who's going to be talking about building robust NISQ simulation. I'll give you a 5-minute warning before your talk time over.
Great, thank you. Thank you for inviting me. It's wonderful to talk about this, especially this new experiment that we have. And the title of this talk is a little bit different than I think what is advertised online, just because I wanted to kind of zoom out a little bit more and spend more time discussing where this particular simulation sits in terms of what I term as building robust NISQ simulation. So if you're familiar with the composition of the theory team at Google, you might know that we have a lot of chemists. And so it's probably not surprising that one of the first simulation experiments we did with the Sycamore chip after the quantum supremacy experiment was doing a chemical simulation. But hopefully this talk shows you how this kind of fits in with a broader simulation picture for condensed matter and other areas. So one question that's been occupying my mind and my life effectively into the future is answering, are we on a path to quantum chemistry simulation or fermionic simulation more broadly, simulation advantage? And so on the bottom of this slide, I've put kind of a timeline of some of the experiments, and Sophia showed some of these already. And I do want to point out that there have been some very impressive hardware demonstrations up until now, but most of them involve fewer than 6 qubits and barely reach the accuracies that are required to decipher some physical process, whether it's a phase of matter or getting a physical bonding energy or things like that. And this isn't a criticism of these particular experiments. It's more to point out that it's extremely difficult to actually get these to work. And so I think that actually frames what our job is in the NISQ era in terms of designing algorithms and error mitigation techniques. So first I want to point out, and this is something that we think about internally at Google, is the NISQ era will be long and it will overlap with error correction. And ideally, we develop strategies that help us at least bring error correction closer. We'd like to learn which strategies are going to work best in terms of effects of noise and error mitigation on our algorithms. For example, we have Baron plateaus work, but also if you were to say, what happens, for example, if you apply one of the, you estimate a gradient, for example, what happens under a global depolarizing channel, namely your signal is going to be exponentially decaying. And then ultimately, how far are we from something classically intractable? I mean, my personal goal is to simulate something, have a chemical simulation advantage similar to a supremacy experiment relatively soon. Okay, so this talk is about an experiment, and so what is the experiment that we did? Simply put, we performed Hartree-Fock on a quantum computer. So this is a mean field theory, but it is an important building block for other condensed matter and many-body simulations. There's actually many modes that you could actually run this experiment in. You could do this in a phase estimation fashion with or without control qubits, or you could run this in a variational quantum eigensolver methodology. And that's the way that we go for this experiment. And the nice thing about this is to really show how to error mitigate these particular circuits. So Hartree-Fock, kind of in a short kind of simulation perspective, is a basis rotation given an orthogonal set of orbitals. And so we can think of each of these, we can think of fermionic modes representing something physical or maybe fictitious, like a orbital here. And these are, I promise you, orthogonal orbitals if you were to integrate over all space. And the basis rotation that I'm talking about is a rotation on the one particle Hilbert space, one particle sector of Fock space, effectively. And so what we're doing is just forming new linear combinations of these basis functions, forming new basis functions. The very nice thing about this particular circuit is that if you formulate it as a unitary, it's quadratic in many body order, like this guy here. That generates this particular dynamics. And this hopefully isn't surprising to everyone given kind of theory of match gates and things like that. But when you couple this with energy minimization, what you do is you get Hartree-Fock theory back. And so that's just this particular normally you formulate Hartree-Fock theory as a self-consistent field theory, but this is kind of the variational formalism, more similar to if you were to try to do Hartree-Fock theory much leveraging Toulous's theorem. Okay, so we know this is classically tractable, so why do it? Well, like I said, basis rotations are kind of everywhere, and I'll spend a large majority of this talk actually explaining where they are, at least in terms of our roadmap, in terms of simulation. We have this optimal compilation. This particular unitary here might look like you need to trotterize it because we know that these particular quadratic fermionic operators don't commute with each other. But we do have an optimal compilation in linear depth using a Givens rotation decomposition. It's a very nice benchmark. I actually like to think of this as a kind of tiny fermionic version of the supremacy experiment. In supremacy, we're taking U to the 2n Haar random matrices and saying, well, what is the fidelity that we can simulate their output weight at? And for this we can actually imagine doing a similar experiment where we take SO2 or SO2n or SUN, where n is the number of qubits, and implement a random unitary that way. And so it's interesting to actually think about like how some of the infrastructure for random circuits actually translates over into this very simple fermionic picture. They're very entangled with respect to qubits. Of course, we know that in a fermionic picture, they're retractable because of this known structure from the closing of the Lie algebra. And I think those are the reasons that actually make this a nice kind of first step in simulation on Sycamore. Okay, so what do I put this slide in actually recently just to kind of draw an analogy to some of the previous work done, experiments done on Sycamore. The supremacy experiment involved circuits that look kind of like this, where we had something called the Sycamore gate, and approximately what it was this I-swap gate, an I-swap-like gate, followed by a C-phase gate of about what is phi is about pi over 4. If you were to do a Cat decomposition on that, or Schmidt decomposition on that, you'll see it has 4 Schmidt coefficients, therefore making it pretty difficult to simulate in a Schrodinger-Feynman kind of style. And like I said previously, we can imagine doing kind of a simpler fermionic version of this, where instead of doing these Sycamore gates, we actually replace them all with match gates. So a match gate has this particular structure where the coefficients at the 4 corners of the gate and the 0, 0, 1, 1 basis form a determinant of the same sign as this internal set B. And so the nice thing about this particular formalism is that we can actually simulate the output of this circuit exactly just with n to the 3 time. So no supercomputer needed. And the gates are actually quite similar to that, what you'll need to do supremacy. And so I think it's kind of a nice secondary step to take going from random circuits to something that actually does simulation for you. Okay, so what's up with my obsession with these basis rotations? So I kind of think forward about what we're going to be doing, at least in the next 2 years, for simulating many body physics and strongly correlated systems. So many times you'll have a Hamiltonian that has these rank 4 interaction terms, kind of like this. And here I have a spin component, but we can imagine spinless fermions as well. And there's one particular strategy that we do know, and this actually turned out to be optimal, is that we can write this particular interaction operator in sum of squares form. Because this V tensor here, if you were to turn this tensor into a supermatrix and then eigenvalue decompose it, you can prove with if this V is the kernel of the Coulomb operator, that this is a positive semi-definite operator. And so we can write it as the sum of squares form. And once in this form, you can do a secondary decomposition and write this as a summation over interaction terms that are just diagonal. And so when you actually think about how this gets translated to a circuit for time evolution, it's actually very nice. You just have a one-body transform followed by something that looks like actually the step of QAOA, the phasing step of the cost function for a classical Hamiltonian. And you can just repeat that. Here's the orange boxes are just the basis rotation that we're studying here. You can also do this for unitary couple cluster and get interesting costs for fault tolerance in this way. We also have efficient strategies for actually measuring the entire Hamiltonian. If we represent them in fermions, we can do the same decomposition. Namely, represent a 4-body term is a sum of local 2-body terms in different bases. And there, what that looks like is just a sequence of, what we'll do is we'll measure at the end of our circuit in a sequence of different bases. And those bases we obtain by measuring them after performing this fermionic one-body rotation. And so we actually have a paper out studying the performance of this, and this graph is a little bit hard to read, but if you were to just compare this strategy to some other techniques about polygrouping and other things like that, the basis rotation strategy always works best by about an order of magnitude, at least for small molecules. And so, of course, in the condensed matter space, where your Hamiltonian is local, this strategy isn't necessary. But for kind of a many-body Hamiltonian with many interaction terms, it's very likely that you'll have to do something like that to have efficient measurements. And very briefly, actually, today appeared on Archive, our paper on simulating the Hubbard model. And so this is kind of the fully interaction version of this particular experiment, the Hartree-Fock experiment. And what it does is it implements Trotter steps it implements dynamics of the Hubbard model, looking at charge and spin separation on Sycamore, and studies a series of error mitigation techniques similar to what we're doing here. But the basis rotation circuits are actually kind of a primitive for this type of simulation, where you might imagine you have a fermionic swap network that I have here on the left, right? It's a sequence of gates where they're always nearest neighbor, and we only do interaction between pairs. And then we follow this with a fermionic swap, namely swapping these two fermionic modes. And so what you're doing is you're implementing unitaries at something like this. And you can see, if you look at the generator from that, that is a local one-body hopping plus a charge-charge interaction. And so this, you can kind of very quickly see, gives rise to the correct Hubbard model dynamics that one would need, or more broadly, TJ models and things like that. Okay, so what does this circuit look like on Sycamore? Hopefully you believe me when I say that these basis rotations are kind of important primitives, at least study here, and at least study their error mitigation. And so what's our starting point? Well, I said I had an optimal compilation, and I'm going to describe that. But what are the gates that we start with on Sycamore? Well, we have this FSIM gate. This is what we get by having a tunable coupler between two transbond qubits. And what we have control over are all of these parameters. So gamma, delta, beta, alpha, effectively, by doing local voltage offsets on either side of the gate pulse. And we have this phasing interaction. Now, ideally, what I would do is just zero out this phase, of course, and then tune the theta such that I'm doing the appropriate rotation for my basis rotation circuit. But of course, I can't do that, and it's very difficult to ask your experimental colleagues to give free control over the gate. And also, that's not exactly quantum programming. That would be much closer to using this as an analog device, and we want to move away from that towards digital simulation, just like Sophia mentioned. So the compilation strategy that we're going to have is we're going to start with this unitary, which we'd like to implement, this basis rotation unitary that's generated by a quadratic Hamiltonian here. Kappa here is anti-symmetric. And what we're going to do is decompose that into a sequence of gates. And we do this via a strategy called the Givens rotation decomposition. And effectively what we're doing is a QR decomposition on the adjoint representation of this particular unitary. And so you do this QR decomposition and you account for particle number symmetries. And what you do is you get a sequence of 2 qubit gates that kind of have this particular structure. Each of those gates, what we do is decompose that into a square root of I swap with some local Z gates, followed by another square root of I swap. And so the compilation strategy here actually is the square root I swap you can think of is the 2 qubit fermionic Fourier transform. And so all we're doing is we're doing a very classic physics trick where we just rotate into the eigenbasis of these two fermionic modes. We do the evolution in the eigenbasis, and then we go back. And these two RZ pi's on either side of this square root of I swap, we'll just turn this into square root I swap dagger. And so it's a very simple compilation. There's no microwave pulses in this. And so we don't have that many error channels in this particular circuit. One thing that can happen, we can see, is that if we perform a slightly poor rotation, that's actually a phasing error on fermionic qubits. And so we need to be able to account for T2 properly here. We can account for T1 by post-selection and other things like that. Yeah, so this is how we have to think about implementing one of these basis rotation transforms on Sycamore. The other thing to point out is that we only need linear connectivity. So none of these gates actually require knowledge or interactions between the qubits that are separated in space by more than nearest neighbor. And that's because when we do the given decomposition, we only do rotations between nearest neighbors, even in this Jordan-Wigner number occupation representation. So this is a very special case. You can't do this in general, but it's another reason why I think these basis rotations are kind of a nice place to start in terms of fermionic simulation. As a pictorial representation, on the left of this circuit here, I have kind of these gray dots, and these are supposed to represent 12 hydrogen atoms. And the initial basis that we start with, each of the qubits is encoding this particular function, just like back on the first slide, right? And the initial basis that we choose is actually just diagonalizing the one particle Hamiltonian. And so you can kind of just count the number of nodes in each of these, and they just correspond to kind of like a particle in a bumpy box. So there's a nice physics perspective on all of these things, and it's a very good place to start in terms of the simulation. Okay, so the thing that we measure, because in all VQEs we know we have our circuit onsets, we have our measurements, and we have our optimization. The thing that we measure is, of course, the expectation value of the Hamiltonian to get our energy, to do energy minimization. And normally in quantum chemistry or in other areas of physics, you need to measure expectation values of these 2-body and 4-body correlators. And most broadly, these actually correspond to the elements of the fermionic reduced density matrices. And so these are the fermionic quantum marginals, and you need to learn via estimation theory all of these particular parameters. Now, for these basis rotation circuits, they're just actually a instance of fermionic Gaussian circuits. In fact, they're just the particle conserving type. And so we actually have a relationship between the elements of the 1-body marginal and the 2-body marginal. Namely, it's this anti-symmetrized product here. And normally you don't have this for arbitrary states, but in this very special case we do. And so we only have to measure these quadratically many fermionic operators. And so that saves us in terms of a lot of measurement costs, and we can focus more on how to do error mitigation at a gate level. A nice thing that actually comes out of measuring just the 1RDM and focusing on basis rotations is that these particular quantum marginals have a very well-known geometry. This is nothing new. It's been around, I think, since the 60s or just when people started studying product onsets. The Hartree-Fock 1RDMs, or 1RDMs corresponding to Gaussian states, are perfectly described by, well, if you're working in a Majorana picture, they're covariance matrices. If you're working in kind of the fermionic operator representation, it's just these reduced density matrices. And so all we need to do to characterize a fermionic Gaussian state is actually just measure this 1RDM, and it comes with this particular geometry. It has a fixed trace. We know it's an idempotent operator or idempotent matrix, and it's positive semi-definite. And so this gives us a way to do error mitigation. When we measure one of these reduced density matrices, we can imagine projecting it back to the set of pure state reduced density matrices. And so I've actually drawn that set here as kind of this square. It does have points. The pure state set is a pointy object. It's not a spectrahedron looking thing. But the idea is that what we're going to do is take some noisy operator and then project it back to the pure set. And in our paper, we show actually how this mitigates T2. The way that they do this in classical quantum chemistry is actually through something called McWeeny purification. Most broadly, what this is it says if your cost operator is the idempotency constraint on the full density matrix and you take the derivative, McWeeny purification is just the gradient step for updating your density matrix. If you contract that down to the 1RDM, you get an iterative solution to a Diophantine equation that look kind of like this. So you're squaring the reduced density matrix and subtracting that from the cubic version. And at the end of the day, if you iterate this technique, you get eigenvalues of the 1RDM that are between 0 and 1, or that are 0 or 1. And so this path here is supposed to kind of project you back to the surface of states that are correspond to idempotent density matrices. I could have, of course, just diagonalized the 1RDM and just rounded all of the eigenvalues to 0 or 1. We don't do that in this case because I can prove a variance bound based on random a Gaussian sampling of all the elements to show that this particular iterative procedure converges, and so that's what we stick with. More generally, you might say, well, of course, this is only for Gaussian states. Why would you do this? Why would you study something like this for more interesting physics simulations? And we do have extensions to this, but we are working on how to apply the pure state constraints, or at least the known pure state constraints, to measured RDMs in a similar fashion. Okay, so how exactly do I do this measurement? And I think this is a particularly clever piece of the experiment, so I wanted to spend a second on it. Our goal is to measure all of these particular correlators. And so what we have is our circuit here on the left, our basis rotation circuit. And if we imagine measuring all nearest neighbor, or all the qubits in the X or Y basis, effectively what we have access to are the first off-diagonal elements of the one RDM. Of course, if we were to measure in the diagonal basis, we could just get all the diagonal elements. Now, the question is, how do I actually acquire information about these off-diagonal elements? Now, in Jordan-Wigner representation, we know that if we translate, for example, this particular element 0, 5 to a qubit picture, we'll have a string of z's in between sigma plus and sigma minus on the 0th qubit and 5th qubit, making a many-body expectation value. That's very prone to error. So what we can do is something else. We can imagine performing fermionic swaps at the end of our circuit. Namely, these are swap operations, but you can imagine that the 1, 1 element of your unitary is a -1 instead of a +1. And what we do is if we actually perform 2 layers of swaps, we can get a new permutation of the qubits, or new permutation of the fermionic modes, and then do the measurements there. And we actually see that we get a different set of off-diagonal elements just by measuring the same same local basis. So that seems nice. We can measure many body terms now at lower weight, but we've made our circuit longer. Another benefit of fermionic Gaussian states is that there's a group homomorphism between the adjoint representation and the full group representation. And so we can actually just combine these two circuits, the fermionic swaps and our original basis rotation, because they're both basis rotation circuits. Swaps are just basis rotation circuits. And so we can continue this procedure and build up the entire RDM by measuring in different permutations that are implemented virtually as different swaps. Okay, so how well does the machine do? I've kind of built up all the theory for this basis rotation and told you a little bit about where this sits in the context of other simulation techniques. So how does Sycamore perform? So first, as a background, the Sycamore chip is a superconducting qubit platform. It has 54 qubits on the chip in a planar array. They're tunably coupled. Here's a picture of the chip and our CEO for scale. And you'll expect when you run on this that you'll get error rates that are approximately of this scale. I think it's really only useful to look at this right column here when you're trying to determine the performance of an algorithm. Namely, you're performing everything simultaneously anyways. The single qubit gates are very good. You'll have almost 3 nines. 2 qubit gates in terms of this cycle are around 99%. So not bad, but can be improved, at least if we're going to move to error correction. And actually readout is the worst. It's around 4% error. But we have improvements here that hopefully will boost this up to around somewhere we'll need for the surface code requirements. So most of the data was collected through Circ, which is our programming platform for using these chips, at least for theorists like me who don't work on the details of how to calibrate all of these things exactly. And OpenFermion, which is our software package for simulating fermions. Okay, so just as kind of a quick teaser, here's a reminder of what the circuit is. We have this basis rotation circuit compiled into squared I swaps and RZs, so no microwave gates, just voltage offsets. That's doing this transformation into this nice new basis that's hopefully minimizing the energy of my product state. You can imagine doing something else also, and this is before we get into the details of the hydrogen chains. Just imagine you start with 2 excitations, and then you just perform a hopping Hamiltonian in the exact same way. So you diagonalize your hopping Hamiltonian, you do a QR decomposition on it, and then you implement the same type of basis rotation circuit, and then you can get this like very nice classical interference pattern. And so on the left, I have just a theory plot that you get from evolving the quantum marginal or your covariance matrix. And then on the right, we have, this should say Sycamore, not rainbow. Internally, we call it rainbow. It gives, well, almost an indistinguishable pattern. There's 132 squared I-swap gates here. And so kind of out of the box, it looks pretty good. But what is the performance required for chemistry? Well, in chemistry, we need very high fidelity circuits. And so it's a much higher bar than just getting kind of a plot that looks kind of close. Let's imagine an experiment that's very simple. We're going to simulate hydrogen chains and their binding. So what we're going to do is we're going to make chains of hydrogen atoms, and we're going to dilate the bonds in between all of the hydrogens.
I think you have about 5 minutes. Sorry.
Great. Okay. Thanks, Gar. So what we're going to do is simulate this binding, and we're going to study different error mitigation techniques. So we can do this for 6, 8, 12 qubits, and this is actually the thing that Sophia showed earlier. And we see that as we layer on different error mitigation, and those are the different colored dots here, we are actually going down to achieving something that is close to what we'd expect in theory. Of course, this is just Hartree-Fock. You can do the actual variational minimization, and that's actually these red points down here, is performed in a similar fashion to actually what Sophia was saying. It's iteratively constructing one of these wave functions. We do it in a slightly different manner, but in the end of the day, it's kind of similar. If you imagine a generator like this, you can take the gradient of this particular operator just by knowing the 1RDM. One of the experiments friends told me that you shouldn't believe anything is happening on your device if you don't see it happen over 2 decades. And so this isn't just noise, we are actually minimizing with respect to the parameters. And so this is kind of a new regime of studying VQEs in the context of the accuracy that would be needed for chemistry. Another nice thing about studying basis rotation circuits is that you get a fidelity witness. So the fidelity witness that we use is actually this particular operator here. It's a conjugation of I minus this particular diagonal operator by the unitary that we're implementing. And this fidelity witness, what it does is it always lower bounds the true fidelity. And so like the supremacy experiment, we have some way of extracting fidelity by just measuring the 1RDM. And so if you're to compare this without doing any error mitigation, so I call it the raw data here, we actually see that we get fidelities, and these are lower bounds, very similar to what we would get just by estimating the gate fidelity from the supremacy experiment. Of course, if you start adding post-selection, this goes up about by 60%. And the reason for that is that we're accounting for particle loss here on all the elements of the RDM, which is a very large channel. For chemistry, you can't lose or gain electrons in this particular system. When we purify, remember I was mentioning that we could actually project to the pure state 1RDMs. What we're doing there is accounting for T2. You can show in a couple lines that if you have a phase error in your fermions, you'll produce an ensemble of these Gaussian states, and purification actually just projects you back to the one with the highest weight. And then, of course, doing variational relaxation, you get another you get another 9 of fidelity. And so I think what this shows you is that one, to do chemistry, will likely need very high fidelity circuits. So these are 3 nines of fidelity for the circuit, the entire circuit. For the largest case for H12, that's 72 square root of I-swaps. And so chemistry is a very difficult area to be working in. But I think other areas, like if you're looking at Hubbard dynamics or things like that, it's actually a little bit lower in terms of the fidelity costs. I'm going to skip this bit because I just want to get to the end and then advertise in the last minute here, and I'll get to the questions. And these are the last 2 slides, kind of where we go. So we've realized kind of that, well, this is a very nice strategy, and we could push this up to about 20 qubits in terms of layering these error mitigation strategies. But that's probably about as far as we can go without starting to include error correction. And I think there's a lot of interesting things we can do by studying the intersection of pure state representability and fermionic error correction and other things like that. And our group has already started to work on that. The Hartree-Fock states are very nice from a benchmark perspective, kind of like a toned down version of the full supremacy experiment. It's very important to develop full error mitigation techniques. And we might actually just need to wait for error correction if we want to do something like in quantum chemistry. And this is actually the last slide. I wanted to put out an advertisement for work that we just put on archive, just appeared on archive today. And that's looking at Fermi Hubbard dynamics and spin charge separation. This was led by my colleague, Zhang Zhang. We used a similar compilation infrastructure. Namely, we have these hopping Hamiltonians. We use the same kind of microwave-free decomposition into FSIM gates to do full Trotter steps. And we do a lot of Trotter steps to get good time evolution here, to get these full kind of dynamic interference patterns for the spin full Hubbard model. And so this has an up and down spin sector. And so this plot down here is actually just to show you that you really need to kind of think about how you can layer on various error mitigation strategies in terms of building a robust NISQ simulator. So first, post-selection, this is just the, this oscillation is the center of mass of your wave packet for a Fermi Hubbard simulation, evolved in time in the up and down sectors. And first, if we do post-selection and then better calibrations and then rescaling, you start to get something that actually looks close to what you would expect in terms of the simulation. And so check out this paper. It builds on the basis rotation work and is kind of the next stepping stone in terms of getting to simulation advantage. And with that, I'll thank everyone for listening and point out some colleagues that were really quite helpful in this. Charles Neal on the experimental side and Vadim Smolyansky for developing a lot of the calibration infrastructure we needed for this particular experiment. I'm happy to take questions. Thank you.
Great. Thank you so much for the wonderful talk, Nick. Are there? We'll open up for questions for the next 15 minutes before we go into the discussion session in the breakout rooms. Maybe to start things off, I had a quick question about the purification, the error mitigation that you mentioned through purification. So what you discussed, it sounded like you're exploiting the structure of this kind of free, the free fermion nature of the state that you're looking at in order to do this error mitigation, right? Because the density matrix has some special structure. Is there a natural way that this error mitigation generalizes or works also when you have interactions, or I guess you guys just looked at the Hubbard model?
Yeah, so we actually don't do error mitigation using quantum marginals in the Hubbard model paper. It's just kind of, it does all the same error mitigation that we do, that was required for the Hartrud-Fock experiment, but and then adds a slightly different twist on some things, so like a reference circuit. But in general, we cannot apply, like you said, we cannot apply the same kind of idempotency trick that we have on the one RDM here, because we do have this, Gaussian states have this very special structure, and we know the pure state constraints for one RDMs of Gaussian states. But there are more general pure state quantum marginal constraints. For ensemble constraints, you can actually apply a similar projection criteria, except that projection procedure now looks like a semi-definite program where you're maintaining the positive semi-definite nature of the two RDM, namely these elements here, with some geometry constraints that come from the algebra of these fermions and things like that. But the computational procedure ends up being a slightly more complicated technique. And so I think for pure state constraints, because we actually know the pure state constraints on the one marginal, that's not sufficient for purifying a two marginal, but they are necessary. And so you might want to start, actually one thing that I'm very interested in is just applying some of those necessary constraints on the one RDM on a more general case to test whether this particular strategy actually works. And so it's a kind of a new area. And there's some other ways you can go by kind of trying to use a swap operation, or the fact that the global density matrix is that important, and then cumulant expansions. And so I think there's kind of an interesting area. The overlap with error correction is also kind of interesting. There's a nice connection of Bacon-Shor codes to two RDMs. Actually, it just proves a very kind of fundamental conjecture in quantum marginal theory. And extending that connection into other areas is, I think, kind of important for applying these techniques to error mitigation. So that's like the long answer to why this is, I think, a reasonable thing to study. On a different note, I did actually want to advertise that if you guys have, or if there are people in the audience who have experimental proposals and would like to run on Sycamore, we've made this public before that we have a very small cohort of collaborators that do run experiments, but we're always interested in hearing new ones, especially as we push into the simulation advantage regime. And I think it's very nice to do. And well, at least for me as a theorist, it was very nice to run an experiment because I worry about a different set of things. And so it's a good learning tool.
Tianzi, you can unmute yourself. It seems like there's another question.
Okay. Nick, do you require particle conservation for your rotation transformation? Can you create?
No, we don't. The circuit here, so in this case, we have a particle conserving circuit, but I could actually put any quadratic Hamiltonian up here as the generator. And for that, it just changes slightly changes the structure of the Lie algebra that I'm working with. So here I'm working with actually SON, so real transformations. If I generalize this to non-charge conserving interactions, or quadratic in Majorana representation, I just get something like SU2n, but n being the number of modes, not the size of Hilbert space. So yeah, this circuit construction through Gibbons rotation generalizes to Bogoliubov transforms, I should say.
Thank you.
Matthew, I think Matthew has the question. Do you want to unmute yourself?
Yeah.
Yeah.
Okay. So when you were looking at the chains of hydrogen atoms, you took an even number of hydrogen atoms. Did you try looking at an odd number? When I guess you would have a spin as well.
We didn't. It would be for this particular case, if we wanted to simulate something in an unrestricted case, we could simulate that. Unrestricted in that not all the spins are paired up. The nice thing about this particular, looking at just even numbers, is that in the restricted Hartree-Fock formalism, we just have to simulate one of the spin sectors. In the other, if we have unrestricted, we'd have to simulate both. Of course, we could do this in series. We don't have to do them at the same time, so it wouldn't double the number of qubits if we make the restriction that the spatial wave functions are the same. But it would just it would double the experiment time effectively. The experiments aren't actually too long. For the 12 qubit experiments, a single energy estimation was pretty quick, like order of like 5 minutes or so, just because we can batch parallelize a lot of measurements. There's only like 13 measurement circuits that we actually need to run for the 12 qubit state, but looking at odd numbers, it would not be that interesting, or it's not that it would be interesting, it's just it can be done with this particular experiment. We just didn't do it for time.
Okay. Thanks.
Oh, I should also mention that getting the gradient of the circuit isn't a generalized thing either. So before we were able to just get the gradient of the 1 RDM and do VQE, or for this experiment, we were able to get the gradient of the 1 RDM or other circuit parameters, these given rotations, with just knowledge of the 1 RDM. But in general, or the covariance matrix, but in general, you cannot do that. You need higher order information. But it would likely just require the 2 RDM, kind of like what Sophia said.
I have a quick question about the fidelity witness that you use. Is that basically, are you just measuring the extent to which multi-point correlations are not, factorizing if what you're, if the state that you're ending up with is not like what you'd expect for a Slater determinant state, then that factorization wouldn't happen, right? Is that kind of what the related to the fidelity witness in any way?
A little bit. So the way I think about the fidelity witness, so the fidelity witness actually comes from a paper by Jens Eiser on Gaussian states and fidelity, estimating fidelity for that particular system. And what it does actually is it exploits the fact that each of these unitaries here. So what you're trying to do is estimate the expectation value of this operator W. But it exploits the fact that each of these unitaries can be implemented on the covariance matrix, right? Because these unitaries are fermionic Gaussian states. So you just measure the covariance matrix, or this 1 RDM, and then you apply these unitaries to it. And then you measure this particular operator, which is just the difference in the occupation vector that you start with. And which is why actually going from the un-error mitigated to just post-selection is a huge jump in fidelity, because this fidelity witness is very heavily weighted towards particle loss. Namely, you're just counting the number of times the local charge isn't equal to the initial state. But what it is doing is it's measuring measuring off-diagonal correlators, but after they recombine into the initial state. And so that's kind of how I see it.
Great. So if there are no other questions, then maybe we can thank Nick again for the great talk, and